That was a periodical modulation of the envelope, but I would like to think about other stimulus options, some of which might lead to an aperiodical modulation. So I'll just draw your attention to this very classical consonant vowel sound, the da sound, which is like quite a well described stimulus for evoking an FFR with an aperiodical envelope modulation. And so I've highlighted the consonant component, the kind of the sharp onset burst related to the da, and then a transition period to the vowel, which is more of an R, that might lead us to, of course, being able to imagine how you could have phase-locked neural activity to that periodical component. And so here I'm just overlaying the envelope, if you like, of that in red here. And so what we're showing here, and this is just figures that are taken from this very well-known and respected publication providing a tutorial on the FFR, or sometimes called the speech ABR, indeed the CABR, the complex ABR. And I guess the thinking behind that terminology is that we have the transient, typically understood ABR component, and we can see that here, the wave 5, and then the A peak, which sort of very similar to the more commonly described SN10 component of the transient ABR. But and that sort of tends to be in response to the onset, the da of the stimulus. But we also can see, if we extend the recording period, these very characteristic peaks, which are labelled with these letterings, the FFR to the aperiodical envelope, and then finally the offset response, which is this last peak here, the O trace. So we have this FFR envelope response, and just to note that I'm displaying, or at least the authors here are displaying, the stimulus as shifted in time so that the peaks line up. But in reality, of course, the stimulus does begin at time point 0, and then there's a latency delay before the neural response occurs. So just having sort of artificially compensated for that latency delay by shifting the stimulus to the right, so that we can see how the response, the envelope response, lines up with the stimulus envelope. And then having a look at the response in this corresponding time domain, then there are these characteristic peaks that seem to correspond with the speech fundamental, the rate essentially of a vocal fold, of vibration, and other harmonic structures of the speech. So to summarize, the ASSR on the left, a periodical envelope fluctuation analyzed in the frequency and the time domain, or the speech ABR on the right, an aperiodical envelope fluctuation analyzed in the speech and potentially the time domain as well. Now let's move the discussion on to some sort of practicalities, if you like, stimulus and recording parameters. So here's an example of the da consonant vowel that we already looked at, and also a ga sort of vowel consonant combination, as a similar consonant but a different, a similar vowel but a different consonant. In terms of transducers, well, inserts would be the typical type of ear-specific transducer one might use, principally because the tube coupling to the ear means the transducer is sort of remote from the scalp a little bit, so some distance. That'll become relevant in a moment when I talk about stimulus artifact. And because also the tube allows a delay to differentiate an artifact from a true response, and of course the ability to do a no-sound trial quite easily. I'll show you that in just a moment. Use of an alternating stimulus might be desirable to try and cancel or minimize contributions like spectral FFR or cochlear microphonics, etc., from the neural sources here that we're interested in. Often with the transient ABR, we'd consider intensity levels in dB NHL, for example, clicks, tone bursts, and CE chirps. But the HL kind of scale relies on there being a reference equivalent threshold SPL, something that we can allow us to relate the SPL value to the average threshold amongst a group of normally hearing individuals for a particular sound and transducer combination. But if these data aren't available, and they're not likely to be for these type of speech signals here that we're talking about, it's not used audiometrically anyway, then that leaves us more in the domain of the just SPL. So they're not likely, these types of sounds, to be displayed in NHL or HL, rather in SPL. And the characteristic way to sort of describe the amplitude or intensity of a stimulus might be the peak-to-peak equivalent method, where the level is related to an easily measurable pure tone, for example. Again, going back to the sort of measurement or management of the stimulus artifact. So we talked about potentially insert phones, and the stimulus artifact being the electromagnetic field generated by the transducer itself. And if this was if this entrained with the electrodes on the scalp, then we could record a response that looked just like the stimulus, but it wasn't in fact a response from the neurons that we're interested in, but rather just the transducer. So we can, of course, the distance is part of the way in which we manage that. The time delay allows us to present the stimulus prior to time point 0 on the latency axis. So we can see here this stimulus in the bottom panel starts at something like -1 or -0.9 milliseconds, and therefore that allows us to spot any stimulus artifact quite easily, because the response should be abnormally early in latency as compared with a true response, which should have happened downstream somewhat. Where, of course, the acoustical stimulus only comes to stimulate the ear, timed to happen at time point 0, and then the ensuing response accordingly. And then we also mentioned the possibility of the no sound trial, which can again help easily distinguish a stimulus artifact from a true response. This would be, for example, from clamping the tube, preventing the acoustical stimulus from stimulating the ear, but not changing in any way the electrical artifact. So by seeing any response still arising at that point, that would obviously implicate an artifact and not a true response. Here's some typical recording parameters. The high pass filter here set to 100. It might be even lower in some cases, perhaps 30 hertz. But ideally a wide frequency filter set. With just sort of standard conventional thought processes around controlling patient noise, ambient noise in the test room, and electrical interference where possible. Without Bayesian weighting, and we'll talk about that in a few moments, it might be wise to have a more stringent artifact reject window than I'm displaying here, to minimize the disruptive effects of noise on the ongoing trace. But with such a recording setup and a stimulus setup as was shown, then here's examples on the Eclipse of the type of FFR that we were just talking about, the envelope following response. So we can see on the two traces, one is for the DAR and one is for the GAR stimulus. And we can see on the left the onset response, the wave 5, and then the A wave. And then as we go downstream, then we can see in both traces, it's clear that there is those ensuing components, in this case the C, the D, and the E components of the in the Krauss, if you like, labeling convention. Now, if we just had a look back at that Krauss article and how our response here aligns up with it, then there is an obvious difference that you might have spotted, which is that we're displaying in the time window only a certain segment of that response. So we can see the A wave and then how the C and the D and the E waves line up. But in the Krauss trace, you can see that there is a pre-stimulus interval, which we're not showing in the bottom trace. And there is, of course, downstream for the longer duration stimulus, 40 milliseconds, I think, this stimulus. There is ensuing components that we're not showing, so the F peak and then the offset response as well. This relates to the way in which the device has an analysis period, which in this case is 30 milliseconds. So, of course, that means that if the stimulus is longer than that, 40 milliseconds or so, then, of course, not all of the response is going to be captured. And this particular 30 milliseconds window I've set to move from +5 to +35, just with the logic that it's enough of a time window to see the transient wave 5 and so on, while sacrificing sort of the pre-onset baseline, but giving us as much of the downstream activity as possible out to around waveform E. But we are missing a couple of components even still, so that the downstream components of the F and the O. Well, why have I done that? It's because there are, in this particular device, fixed display windows, and the one that comes closest to my needs is this 30 milliseconds window. And I'll just try and unpack that a little bit in a couple of slides' time. But without being able to see the pre-stimulus baseline, then it's difficult visually to judge noise, or residual noise, but we do have an objective residual noise indicator on this device. And so both of these traces have been averaged down to a similar level, 28 nanovolts or so. And we also have other sort of analyses tools, so we can tell objectively that there is clearly a repeatable response there, because we have a very high FMP ratio, and we also have a high degree of reproducibility between the A and the B curves. Interestingly, the polarity of the traces doesn't reverse when we separate the response into the rarefaction and condensation components, and this shows you that it's an envelope response rather than following the spectral content of the sound like we were showing earlier. A moment to mention Bayesian weighting. We don't need to talk about it in great detail, but it's a way to, of course, improve the robustness against fluctuating noise that's non-stable, and it's very important, I would say, in reaching a criterion-based residual noise level rather than just some sort of criterion number of sweeps, which may not account for non-stationary noise. And this is one of my favorite quotes from the ABR literature. I'm talking here in this case about transient ABRs, but of course the same concept applies to the frequency following response. So if measuring these responses in the way that I've tried to show, then please do consider the need to reach a criterion low residual noise level in order to resolve the response against the background residual noise. Now, why about the 30 milliseconds time window? So ABR signals, like we're showing, are usually very oversampled with regards to the bandwidth of the signal. So sampling frequencies of sort of 30 kilohertz and more are very typically used by ABR devices, but the information content of the ABR signal isn't very high above around 2 kilohertz. And so normally the lower fence for sampling rate would be double the upper level of the frequency, upper point of the frequency content. So if it was a 2 kilohertz signal up to 2 kilohertz, then a sampling frequency of 4 kilohertz or higher should be sufficient, and yet we use perhaps 30 kilohertz or more. So that's what I mean by oversampled. Oversampling, talking about the number of points used to digitize the analog signal. And here we can see as the number of points increases, then the digital representation of the analog signal becomes more and more, the resolution becomes more and more improved. So going back to the 30 millisecond time window that we were talking about earlier, then the interacoustics eclipse uses a fixed number of sampling points. And so if we have a shorter window, then the sampling rate is higher. And if we have a longer recording window, then those fixed number of sampling points needs to convey the information from a longer period of time, so the sampling rate goes down. So so the eclipse does have a range of different sampling windows that we could choose from, but at the expense of rate. And so here we have the same response that's recorded from the same individual, but on a different occasion in the lower trace, but using the wider sampling window of 120 milliseconds. This is more than enough now to show the response to the stimulus here, the DAR stimulus, in its entirety. So the onset response and all of the different components, as I'm showing lined up with the example at the top. But as we can see, as the response is downsampled, then the resolution tends to reduce, and so you could say the aesthetic quality of the waveform isn't quite the same as in that middle panel, where at the expense of not being able to observe some of the peaks of the waveform, but we do see a higher resolution version, if you like, of the bits that we do see. So we have a certain compromise to make with this device in that respect. And if it was the case of showing response present or absent, then you might, of course, be inclined to be satisfied with that middle trace, the 30 milliseconds recording window. But if it was to the ability to see all of the peaks, then a wider recording window is needed. And then here we're talking about how to so in the time domain, as we saw on the screen previously, then we can analyze basic components like presence or absence of the waveforms, amplitude and latency, and certain other things such as the cross correlation between two waveforms. But if one wants to look at the frequency content, then this requires a certain post hoc or offline analyses, and Interacoustics have provided a very convenient tool for a first pass at this. It's simply an Excel spreadsheet which has been designed to provide a frequency analysis of imported stimuli. So what one would do is they would export the traces from their Eclipse device, export them for offline analysis, import them into their third-party software. It could be this Excel tool that's freely available on request from Interacoustics, or it could be some other third-party analysis software in order to, as we're showing on the right-hand side of the trace of the screen here, analyze the frequency components. Now, just in closing, then we will just sort of nod towards potential clinical applications from these frequency following responses. So firstly, going back to the neurophonic that we were talking about earlier in the talk. Now, over recent years, there's been an expansion or a widening, if you like, of eligibility for implantation, and you'll increasingly see individuals with relatively good residual low-frequency hearing being potential candidates for cochlear implantation. And a basic sort of criteria is shown with this audiogram on the left, where someone might have even mild to moderate sensitivity levels in the low frequency region, and this leads to a desire to monitor in real time or as close to real time as possible during an implantation phase to address a high frequency loss, the integrity of the low frequency hearing, of course with the intention ideally of hearing preservation for that lower frequency acoustical sensitivity. And although sometimes this is the sort of cochlear implant response telemetry is used to try and assess this from the point of view of responses directly measured from the implant itself, it's also at least feasible to consider the FFR, the auditory nerve neurophonic, as or the putative neurophonic, as a means to do this very quickly. And so here we have so not quite real time, but very close to real time. And of course this is very sensitive to low frequency hearing, unlike some of the transient responses. And so here we have just a reference to a paper by Cook and others showing the potential for, at least in this case, transtympanic recording sites to pick up a neurophonic response within just a few hundred sweeps, which should be very close to real time in the period of time it takes to obtain that, and therefore give feedback, for example, to the surgeon about the course of the surgery and the efforts to preserve low frequency hearing. So that's a potential for that's one clinical a potential clinical application. Apologies for the somewhat wordy slide here, but of course the FFR is a non-invasive means of reliably measuring the fidelity and precision of sound encoding. And so there are a whole host of potential clinical applications here where there might be some reason to suspect that these features in someone's auditory system are impaired. So some people with developmental speech and language disorders, how that might change, for example, with an intervention. These are all potential clinical applications of the FFR. Although I'm not aware of any routine use in this way yet. I think it's still in that sort of developmental phase at the moment. Finally, just in closing, we'll talk about validation of hearing aid fittings. So here we see a sound field presentation of a stimulus, and we do that so that a child wearing a hearing aid, the hearing aid is therefore in the sound path, and we can use potentially the FFR to ensure that the frequency or the acoustical components of a sound are well represented in that child's auditory system, and that might lead to a positive validation, if you like, of the hearing aid fitting. So in terms of the time frame here, we can see, of course, in the early phases of a child's development, the conventional existing applications of the ABR and the ASSR and so on, leading to a hearing aid fitting. But downstream of that, but at some point prior to when behavioral assessment might be feasible, then an objective means such as the FFR could be useful. And that's where, of course, the eclipse might come in addition to which a separate issue, the need to re-verify the hearing aid due to growth of the ear canal. And there are some relatively recent papers just looking at this, so I'll just briefly spend some time summarizing that. So it's been looked at both using the ASSR, at least feasibility in principle, so proof of concept, as well as the FFR that we were just talking about to a speech signal. So just briefly, the top left panel, this paper from Largerson and others, they used a conventional ASSR stimulus, like a chirp, and also one that was modified to reflect speech patterns of aperiodical stimulation. And the darker symbols, the gray symbols, show the response amplitude to a conventional ASSR, and then the lighter circles show the response amplitude, somewhat smaller, but still very robustly there at the fundamental frequency, in this case, of the modified stimulus, showing feasibility. Equally, test time, so slightly smaller amplitude just leads to a slightly longer test time, but nonetheless, I think most would agree that it's clearly a potential there, so sort of a proof of concept type of paper. So what they were doing here is they were comparing the ASSR performance between in a group of normally hearing adults, sort of a within subjects design. There, but equally on the bottom right, another contribution, a similar notion showing components of the FFR and how they could be used to index the ability of an aided auditory system to encode the speech properties of a sound, and how the settings of a hearing aid could be tuned to ensure that those qualities are most clearly resolved.